This is an example demonstrating the contradictory premises rule. We call it happy. The story is this: anyone who is funny is not sad. There is someone who is sad while everyone is happy. Thus, someone is taller than everyone. Let's begin by defining f of x to be x is funny, s of x to be x is sad, and t of x and y to be x is taller than y. From the story and these definitions, we may represent the two premises as: for all x, f of x implies not s of x, that is, anyone who is funny is not sad, and there exists an x such that for all y, f of y and s of x, that is, there is someone who is sad while everyone is happy. The conclusion we seek is there exists an x such that for all y, t of x and y, that is, someone is taller than everyone. Once again, symbolically, the premises are: for all x, f of x implies not s of x, and there exists an x such that for all y, f of y and s of x. The conclusion is there exists an x such that for all y, t of x and y. So, how would we construct a proof of this? Let's begin by looking at the conclusion. The conclusion says that there exists an x such that for all y, h of x and y, but there is no mention of the predicate h in the premises. Previously, we said it appears that this conclusion has arisen out of thin air. It was also said that in such cases, either the contradictory premises or addition rules must be applied. Let's see if we can use contradictory premises. To do so, we look at the two premises and, for the moment, ignore the quantifications. We see f and s in the second premise, and f implies not s in the first. Clearly, having f from the second premise would then imply not s from the first. But then we would have not s and s holding at the same time. Those would be our contradictory premises. But we ignored the quantifications. The only one that might cause trouble is the existential. There exists an x in premise 2. Let's make sure to deal with that one first, since both of the other quantifications are universal. If you would like to complete this proof on your own, please pause this video now. On line 1, we place our second premise. There exists an x such that for all y, f of y and s of x. On line 2, we existentially instantiate line 1 with x being replaced by a star. This results in for all y, f of y and s of a star. On line 3, we universally instantiate line 2 with y being replaced by the same a star. This results in f of a star and s of a star. Now let's introduce the first premise onto line 4. We have for all x, f of x implies not s of x. On line 5, we universally instantiate line 4 with x being replaced by a star. This results in f of a star implies not s of a star. On line 6, we simplify line 3 to f of a star. Then use modus ponens on line 7 to get not s of a star. That used lines 5 and 6. Another simplification from line 3 results in s of a star. This is placed on line 8. Now we see the contradictory premises in lines 7 and 8, so we are justified in writing any valid formula on line 9. The one we choose is there exists an x such that for all y, h of x and y. That was the conclusion we sought, and this concludes the proof.